dependence between the Cartesian variables, and that gets wrapped into using this chain rule for McNerney. For me, the dependence on the differentiation in the manifold is all folded into this composition with the patch, right? This puts the calculation on the manifold and builds the structure of the manifold we're dealing with into the calculus. But at the same time, it's totally natural. And you see why my way is better, because at the end of the day, if we can write functions on the manifold in terms of natural coordinate expressions, differentiation is a piece of cake. We just do ordinary calculus on those expressions, and that's it. You won't find this cleanly stated in books much. All right, so, yeah.
Can you just explain real quick how you go to r plus a cosine b squared over x squared to 1 over cosine squared b?
Yeah, it's just that the x is this.
Okay.
So when you square that, you've got what we already have and a leftover cosine squared.
Oh, okay.
So this r plus a cosine v, the sort of big,
So you plug in x for the original.
yeah,
And then you have,
yeah.
okay, got it.
So I think, I mean, hopefully it's less mystical to you now, right? I mean, it's actually a pain to actually exhibit. I mean, this is why I couldn't just think of an example for you. There's some notational struggles I had to deal with. Now I've dealt with them, and so I'm not getting stuck on them at the moment. The next thing to talk about is when we have a function from a manifold to another manifold n, right? And we want to talk about the so-called push forward at a point P. And that's going to give us something that goes from the tangent space at P at M to the tangent space at F of P of N. And he says that this gives us a vector field if we allow P to vary. But he makes no condition on the injectivity of F. That's not right. But anyway. So here's how are we going to define it is my question. So I like to, my notation, guys, is this. Or, well, I don't know. Maybe I can't remember. I got to look at my notes, but it's either this or that. I mean, so to me, that's what this is. But a lot of books use this for the push forward, right? So how's this going to work? Supposedly, let's think about it. The push forward at P acting on a derivation x at P, right? This should be what? This should be an element of the tangent space to F of P at N, where, again, N is M and N are both manifolds, okay? So what does it take to be in here? This means that these are derivations on what? C infinity, where? F of P, right? They're derivations on the smooth functions defined near F of P and N. These are smooth functions from some neighborhood of F of P, which is a subset of N to the reals. We're always dealing with real value functions. So how should we define this? I mean, what would this, so in other words, to define this, we need to feed it this whole thing, feed it a smooth function g, let g be an element of, smooth functions defined near F of P. So what should this be? Let me get the ball rolling. XP xp, what did you say? xp, let's see here. Do you want to look at f composed with g, or do you want to look at g composed with f? Right, because this one, right? Because exactly this takes in what? Takes in p, spits out f of p, and then g takes f of p and spits out a real number. So this is the sort of thing we could feed to x of p logically. So g composed with f, yeah. Congratulations, you just defined the push forward. That's it. Yep. Definition. Now, to actually calculate it in terms of coordinates, the thing is, this, let's call this thing v first, just for the sake of discussion. This is really v at f of p, right? And so v, and I'm just going to call it v because I'm getting really tired of writing v of f of p, so let me just say just v. Let me drop the f of p, if that's okay with you guys. And that was going to be the sum j equals 1 to m, oh, I'm sorry, n, right, of v of y upper j, see, I learned eventually, partial y upper j at f of p. But on the other hand, the x, right, it can be written as the sum I equals 1 to n of xp of x upper I partial x xi at p. The natural question to ask, of course, is like, how do these guys relate to those guys? Come on, you idiot. Come on, I want to use this stupid projector. That is, no, this is something less interesting. I accidentally hit the video mute button before I hit the power button, which confused it, and now it has the red circle of disgrumblement. Ha-ha! It turns out these two are related by the Jacobian matrix of the function, essentially. But that notion has to be fed through the coordinates. It's like the partial derivative of the jth component function of f with respect to the ith coordinate function of x, and then weighted with these components, that gives you those components. But I have some explicit formulas to show you that will perhaps, oh, yeah, funny thing, you don't plug it in, it doesn't work. Here. Now, you do not need to try to write these down. I sent you a link to this, and really you just want to try to understand with me. So relax, this is it for today. If we get through this, we're done. So this example, what I want to look at is a function from GL2 to SL2. So GL2 is what? We prove this, it's open, right? And you know what? It's also connected. Wait a minute, that's not true. It's disconnected. But it's got two components, the positive and negative determinants. Matrices, it's got two components actually. Inside the positive component, you'll find SL2 or SLN for n. It is in fact a normal subgroup, yes. Whatever that means. It's not like those abnormal subgroups. No, we don't want to make those kind of judgment calls in here, right? I mean, judge not lest you be judged, right? Let's see here. So anyway, so this is a nice coordinate system. The point is GL2 is an open subset of the 2 by 2 matrices, which means it's open subsets of like R3 are three-dimensional. Open subsets of R2 are two-dimensional. So that means that GL2 is a four-dimensional manifold. And so there it is. And you can just use the component chart for the chart. On the other hand, SL2 it's a 2 by 2 matrix, but there's a condition. There's one real equation, the determinant being 1, which means it's a hypersurface in this set of two. It's a three-dimensional submanifold of GL2, in fact. And well, for my purposes here, I want to use a coordinate system. So you just got to come up with a coordinate system which respects that determinant condition. And a nice one to use is just B11, B12, B21. And then with that, B22 is given by them according to this. This only works for the matrices which have first 1, component non-zero. So this chart covers part of SL2, but not all of it. Okay? In particular, it'll cover the part of SL2 that's got the identity matrix in it, because the identity matrix has got 1, non-zero, which means we can define B22 like that. So, okay, good. Now, the inverse to the coordinate chart is this. So that's actually a patch whose image gives you some subset of SL2. And you can see that that's a good mapping because it's a determinant, works out like it's supposed to. It gives you 1, which means that this mapping's into SL2. Okay, I'm just making sure that my coordinate chart is actually like legit. Great. The function, oh, I already told you what function I want to look at. I decided I'm going to look at this one right here. The function I'm going to look at is the matrix squared divided by the determinant of A. And that makes sense because the determinant of A squared is the determinant of A squared. So they divide to give this 1. So this mapping goes from GL2 to SL2. It's a well-defined map. And it's also awful. So yeah. So yeah, there's the local coordinate representative of F. Oh, I'm not sure it's even that yet. Well, yeah. And so, yeah, so then I calculate the push forward of this one, and then acting on that actually works out to, I take Y11 composed with F, and I partial. Yeah, I think the next thing I should have, what would this mean? Oh, I'm sorry, I'm running out of energy here. But this can be calculated like that. I'll try to, maybe next class, I'll try to come back and derive the formula here that I'm using in the abstract. The point is, so this gives me the 1, component of what that maps to. When I work out this gives me the 1, 2 component of what the 1, 1 coordinate derivation in GL2 maps to, which is B, that's A. And then finally, so I got 1, 1, I got the 1, 1 component, I got the 1, 2 component, I got the 2, 1 component down here, A, B, and C. So what this calculation altogether does for me, in all of its horrible glory, shows me that the push forward of partial x11 under this mapping F is that. And this A and B and C are not related to that A, these are the monstrosities C, A, and B up there. It is so very horrible, this example. But hey, at least I didn't assign it to you for homework, right? Yes?
Were you doing like the uppers and lowers thing in that example? Or was your uppers like...
Yes, I'm doing the uppers thing here, yeah. See, I got x upper 1, 1, y upper 2, 1, yeah. There is actually some content to that, which I will explain as time goes on. It doesn't really hurt us to confuse the two at the moment. It doesn't really, we're not using it yet, so it won't hurt us until it does. This is a friendlier example. So here we have from GL2 to R2. I said, you know what, one honest to goodness manifold is enough. Let's look at a mapping from a manifold to R2. At least for R2, we can use the standard Cartesian coordinates. That takes away half of the nastiness. All right, and my formula is going to be determinant of A, trace of A, which are fun, exciting things about matrices, right? So there's the formula for it, A, B, C, D, AD minus BC, A plus D. And so in terms of coordinates, I suppose that's my formula. So this is the first component function of F. That's the second component function of F. And so there's a picture of what's going on. And so the way we calculate the push forward of xp under F is we take xp of G composed with F. Thanks to you guys for making that definition. And it's good that it agrees with this one from like 5 years ago this is from 2011, so 6 years ago. Man, I'm old. Anyway, so to calculate this, apparently I take y1 composed with F of that. Now this just means the first component function of F. In this case, the Cartesian first component of F, which is exactly this guy, which is why I put this guy right there, rather. And then you can partial differentiate with respect to that. Now here, I am using what we derived today, that you can do partial differentiation on a manifold with respect to coordinates, just like ordinary calculus once you write functions on manifold in terms of coordinates on the manifold. Anyway, so that's x22. Likewise, the second component of x11 is just differentiating that piece, which gives me 1. And let's see here. I also figure out for 1, 2, the first and second components of 1, 2, and also the first and second components of where 2, 2 maps to, and then also the 2 1s are over here. So I calculate where every different basis derivation for GL2. There's the 1, 1, the 1, 2, the 2, 1, the 2, 2. It's 4-dimensional. I calculate where each one of those goes to, and altogether, so based on those calculations I just did, I see that x11 pushes forward to that, x12 pushes to that, x21 pushes to that, and x22 pushes forward to that. So that is the push forward under F of this mapping. You could instead write it like this. You could say, okay, I'm going to take an arbitrary vector. It's got these components weighted against the 1, 1, 1, 2, 2, 1, 2, 2 coordinate basis. And so I can use linearity. I can pull that out. See, knowing what happens to the basis tells me where to map anything else to, through the usual linear algebra. There it is in all of its glory. So you work that out. 1 and 2. Here's the 1. Here's the 2. I mean, here's 1, 1, 1, 2, 2, 1, 2, 2. And rearranging stuff, you can see it's really, if I look at just the coordinate, this is the first coordinate of the push forward of VA. That's the second coordinate of the push forward of VA. And you see I'm obtaining what I was calling this vector. I'm obtaining this vector from this matrix times the components. This V1 through, it's unfortunate, but this V11 through that would be analogous to this guy. So I'm saying I take this, I multiply take this and multiply by that matrix, I get that out. What is this matrix? That's the Jacobian matrix for the manifold map. It's DAF. It's this matrix. It's partial derivatives of the component functions of the map with respect to the coordinates. That's exactly what that is. Which is obvious if you look at f. The second component of f is x11 plus x22. That's where these are coming from. The first thing is the determinant. So the determinant's popping out these things. Two of them got minuses, two of them don't. It's the determinant formula that's coming from. Oh, and I'm fresh out of examples, so I do have one other example to go through. Thank you, liar, liar, pants on fire. You said we were done. There's some really interesting examples in this, which I'm not going to talk about right now. The one I did want to point you to was just this one. Travis, you might like this one. This connects with Calculus 3. It would be wrong for me not to. I just forgot until I got to this point that I should tell you about it, but this takes me all of like 3 minutes. So if we look at F being the coordinate change map on R2, going from R2 to R2, going from R theta R2 to XY R2 according to this map, I can think about pushing forward partial R and partial theta. Those are the coordinate derivations here. And when I do that and I sort through this push forward thing, do the calculation, I get cosine theta partial x, sine theta partial y. All right, well, what is this? If you do the calculation for theta in the traditional calculus 3 notation, it looks like this. Partial x, partial theta, partial y, partial theta, partial x, partial y. You recognize this. This is what we do changing coordinates in calculus 3, right? This is how we change from a partial theta to a partial x and partial y with respect to the right chain rule. But my point is that that's actually the push forward. Technically, this is really the push forward of partial theta at p to the corresponding derivation in terms of partial x and partial y at, f of p. So these calculations we did back in calculus 3, you can think of them actually as being push forwards. Or another way to look at it is the push forward is the abstraction of the notion of coordinate change in some sense. It allows us a way to change, one thing we can do is use it to change coordinates on a vector, on a derivation. It's more than just that, but this is one interpretation of it, which I have at times found comforting. So this example 8.35, it might be useful for you to look at, but all right, enough. Be gone. So what are we doing next time? I still have more chapter 3 to cover. Next time I need to talk about integral vector fields and the notion of diffeomorphisms built from them, right? That might not take a whole day. Hopefully we'll be on to chapter 3, chapter 4, which is fun stuff. So now, I'm not assigning you any homework on this until after the test. When's the test? 16th. So the homework on this will be much later. I'm hoping that we have time to really, I'm telling you a lot of stuff. It's probably only going to result in like 10 homework problems.
What does mission 4 do?
11.
11? So you just wanted us to hand it to you during like your office hours?
Yeah. And then so that if you get it to me the middle of the week, then I should be able to get Jess to grade it. Hopefully I can get it back to you like Friday that week is my target. Hope Jess isn't busy. Maybe I'll just grade it. Everybody gets 100. Woo! If you have questions about mission 4, don't hesitate to ask me. I'm happy to help.